Okay. Uh, the last time we'll talk about this set of data. This set of data is actually the monthly, the time series based upon each particular month. Okay, we have 12. Then 12 we can average, and average we get a standard deviation. So this actually is the data that most people use for discussion of global warming. And as I said, because this is downsampled, 1 to 12 downsampled, we have January, February, all the way to December. Okay. If we average all the January, what happened? If we average all the January, this is what we got. Yeah. All the January, all the February, all the March, and then you can still see that July is slightly warmer. The fact that July is slightly warmer is not surprising because July should be a lot more warmer. This is only 0.3 degree warmer. July should be 20 degree, 30 degree warmer than winter. But what happened is that the seasonal cycle has already been taken off. So this is why this is called the global surface temperature anomaly. It means beyond the normal. The normal is defined by the average of 30 years. So after you take the 30 years away, it's not clean. Okay, you still see seasonal variation. Not only see seasonal variation, each July, if we take July, we average, and July has a standard deviation. July standard deviation is much smaller than the January standard deviation. And we discussed that last time too. Winter time, when the temperature is cold, the atmosphere has less heat contents. So its heat inertia is small, so it's subject to large fluctuation. In the winter time, it's relatively dry in most of the place, not in Taipei. Taipei, winter time, it's raining season. But when you have dry air and cold air, it fluctuates more. And this gives me an impression that this data is not very clean. If the data is clean after 150 years, we should have a very smooth curve rather than very jagged curve like this. So let's see what happened. If we take the whole data, this data is monthly data. If we take the whole data, let's don't do anything, just do a Fourier spectrum. What happened is that you see a big peak still come up. Now we have already said this is an anomaly, anomaly. If we have anomaly, we should not have a yearly cycle. The yearly cycle stick out. That means it's not clean. Not only that, beyond 1 year, the information is almost no information. Yeah, it's not completely white. If it's complete white, it should be flat. It's not complete white. It's a little bit red. Yeah, slightly slanted. That means it has a little bit longer wave than shorter waves. Yeah, so this must be the noise that we got. We can see the noise in our data. At the beginning, the station distribution is not very good. So we do have a lot of scattering at the beginning. So if we want to clean up the data, because I do not know what kind of annual cycle they remove, it's very difficult for me to go ahead and remove that spike. Okay. But I can certainly clean up by throw away this red noise beyond yearly cycle. So what I did was, the annual cycle is actually 12-to-1 downsample. In spite of removal of climatologic mean, there's still a seasonal cycle appear in 1 year. And seasonal variation and variance are somewhat irregular, and the data contains information before 1 year. In other words, this is 1 year. If we want to do annual cycle, we should not have anything beyond shorter than 1 year. So we decide to filter the data. the way that we filter data, traditional filter is by remove certain frequency, and that may actually distort the fundamental. Yeah, so noise spike are local in time. Signal local in time has a broad spectrum component. So we decided to use HHT to do a filter. This is how I use HHT to filter it. What I did was I used intermittency here. Yeah, intermittency, I use two extrema to zero crossing at 2. That means the wave, actually, half wave is 2. The whole wave is 4 months. I use 4 months, I remove that much, and then use 8 months. I use 9 times. I use it once, twice, 3, 9 times news, totally nothing. Shorter than 8 months. Beyond 8 months, I dare not to touch because it might be a yearly cycle, whatever. So after I totally remove 8 months signal, then I said that I will not do anything. Just let the EMD go through that. So this part is shorter than a year. And if I remove that part, the data should be cleaner. So this is what's left in the beyond 8 months. Presumably this should be a year and so on. So if I do that, I sum up all the things that I removed shorter than 8 years. This is the sum of that value. The sum of that value is, I displace it a little bit lower. The sum of that value is very big. It's almost comparable to the signal itself. And this is the original data averaged. This is the smoothed. You can see that the smoothed data and the original data, there's a lots of difference over here and a very small difference in the recent period. Not only that, the data that we removed, it's a lot of energy here rather than over here. That means we have a lot of noise in this region, and if you look, we have a little bit more energy here and a little bit more here. These are the wartime, First World War and Second World War. So in this way, we indeed remove a lot of noise. But then we have to check. See, if we threw this away, did we influence any of the information? To check that, we did another spectrum. This is the spectrum that we removed. The spectrum we removed is totally flat. That means we remove a white spectrum. If we remove white spectrum, we did not remove any information. Okay. Then what happened to the data? This is the original spectrum of the original data. This is the spectrum after we remove this. So in other words, what we removed here is actually we removed the noise. The noise is shorter than, the wavelengths are all shorter than a year. If we remove noise shorter than a year, then we do a yearly average. It should not influence our answer. Right? We remove the wave shorter than a year. Why we want to remove data shorter than a year before we take a yearly average? Because if you have shorter wave, shorter than a year, but then you do a 12-to-1 downsample, you still will encounter fluctuations shorter than a year. January may be here, February may be here, March may be here. So this fluctuation gives you a false data as if you do have a small wave. And that shorter, this gives you alias. This shorter wave has to be removed. So once we remove that, we find that whatever we remove contains no information. It's totally noise. And the clean up the spectrum looks like the red and we did not impact anything of signal longer than a year, then from that data, we downsample, we get this. This is much cleaner than the previous downsample signal. And this data, compared to the previous downsample, this and that, you see the difference. So using EMD, we can clean it. After we clean it, we do an annual average. The annual average is the red, and the previous annual average is the blue. So the red and blue still going along about the same trend, the same usual fluctuation. The difference is given by this. The difference has an amplitude about 0.1 degree. Yeah, it's not much. The most difference is here. That means at the beginning, the data is not very good, and we remove that. And when you come to the recent time, the difference is small. The difference is pretty big over here, around the Second World War. Yeah, the First World War is smaller, influence is smaller. This difference is not much, 0.1 degree. But remember, over 100 years, 150 years, the global temperature increased 0.7 degree. So this is about 15%. Yeah. So this is the way we clean it. After we clean it, we can see previously the variance of the temperature. Previously, the variance of temperature is very high here. And it has a trend coming down. And that makes people say that they want to reject this data because this data is too noisy. Yeah. After we clean, this variance dropped to here. It's almost flat. So now we have a clean set of data throughout the whole region. Here is slightly higher, but it's a substantial improvement over the uncleaned. And now, after we downsample to monthly, and we do monthly mean, the new monthly mean looks like this. The previous monthly mean looked like this. This means that after we clean up the monthly fluctuation, the noise, the month, the season come out very nice. So after 150 years, we know which month is warmer, which month is colder. Not only that, the seasonal variation is also very smooth. Yeah. So after you get rid of some noise, you can actually get a much cleaner set of data. Yeah. So the global surface temperature anomaly should not be derived from a simple annual average because there are noise in the data. Yeah. We cannot just say that we get the data, we say, all right, once I average, then the noise below 1 year or shorter than 1 year all get averaged out. You will not do that because the fluctuation of the noise is different year to year. So the noise, whatever the noise pollution is still there. Noise period shorter than 1 year could have caused the alias of downsampling. Yeah. So you have a fluctuation. Sometimes you hit downsample, you hit the high. Sometimes you hit the valley. So that gives you the noise, even you downsample that. Yeah. Smooth data by remove shorter than 8 months actually helped a lot. Yeah. So this is the climate change, and actually we'll talk about the trend. In climate change, we talk about the trend. Yeah. This trend, the original temperature trend is given in this paper, Zakos, in 2001. Yeah. This data is a collection of hundreds of stations globally. From what? from marine sediment. In the ocean, there's sediment, you get a sediment. In the sediment, there are living cells, skeleton of the living cells. And the skeleton of living cells has oxygen 18 isotope. It has oxygen 16, oxygen atomic weight is 16. But this is oxygen 18 isotope. Oxygen 18 always exists, but oxygen 18 is a little bit heavier than oxygen 16. So when temperature fluctuates, oxygen 16 becomes much more active than oxygen 18. So in high temperature, the oxygen 16 proportion of 16 should be more than 18. So you take the ratio, then you find that the oxygen 18 percentage is low when temperature is high, it's high when temperature is low. Yeah. So as a result, we can use oxygen 18 to oxygen 16 ratio as a temperature proxy. And this, of course, you have to calibrate, and after the calibration, you get a curve. Okay, you get a set of that temperature data. This set of temperature data is the most complete one up to now, with more than 150 stations distributed globally from marine sediment. How long a period covered? It covered almost to 70 million. 70 million, yeah. 65 million is a big event. 65 million is when dinosaurs disappeared. And the current theory is that a big meteor hit the Earth and wipe out all the dinosaurs at this time. Yeah. And dinosaurs dominated the Earth from 230 million until this time. Dinosaurs dominated the Earth for 100 million years. 1亿5千万年. Yeah, all the way dominated to this, suddenly disappeared. After it disappeared, however, you see the temperature here and the temperature here. If, whoops, sorry, I don't know why we cannot see that. Can we? It's over there. This is oxygen 18. This is the temperature scale. This is a temperature scale. And we set our present temperature to be 0, arbitrarily, okay? To be mean, to be 0. And then this point actually is 12 degrees warmer than now. Yeah. If you look at this, this is our temperature. Our temperature keeps dropping, coming up, drop. We are now here. So compare that to this place, it's 12 degrees. Yeah. So our temperature right now is much colder. Using this scale from 65 million to now, our temperature is coldest. Yeah. And not only that, geologists and paleoclimatologists, long before people worry about the global warming, named this period, which is the highest temperature period, as the early Eocene climate optimum. Early Eocene means 死新. This is a geological period, and climate optimum means the best temperature. Yeah. Why we think this is a climate optimum? Because after dinosaurs died away, what happened is mammal come up. Yeah, dinosaur is vertebrate, is 脊椎动物 vertebrate. Yeah, but it's not mammal. We are mammal. All the animals that we see now, most of the animals walk on 4 legs are mammal, like a cow, horse, dog, cats. They're all mammal. Mammal appeared. The earliest mammal fossil appears in this around this range. Yeah. The high temperature actually is conducive for the new species to propagate. Yeah. Another thing on the side I can tell you, the Earth is not always covered with ice, or Earth is not always have any ice at all. Beyond 30 million years ago, the Earth has zero ice. The whole globe has no ice. Ice start to appear a little bit here and there because of this part has a glaciation. This glaciation indicates ice only appear in the Antarctic, the southern hemisphere. Yeah. Northern hemisphere, our Arctic ice, 北极的冰, appears only here. Start from here. This is very recent. It's about 3 to 5 million years ago. Beyond that, the North Pole has no ice. Yeah, no permanent ice. The reason that we have that is plate tectonic. It's the movement of the Earth. Atlantic Ocean started 2 million years ago. I'm sorry, 200 million years ago. I forget about the order of. This continent used to be one. This used to be one. And this started to split 200 million years ago. And the speed is pretty constant based on the geomagnetic and the radioactive dating of the rocks. There's a continental mid-Atlantic ridge, which is the place that push push the continent away. So around 50 million years ago, notice that Australia, notice here, this is India continent. This is the equator. India continent just split off from Africa. Yeah, still in southern hemisphere. Yeah, and that's 69 million years ago. That's when the data first started. And by 50 million years ago, which is the mammals start to thrive. This is Australia. Australia is still pretty far south, and it's not connected to the Antarctic, not connected to the Nanji. But this is separated by a shallow ocean, a shallow sea. The ocean is very, very shallow. So the ocean current come around here. This drag is also very shallow. It's hard to get back. So the ocean current can only flow around here. So you come to the cold and then have to go to the warm spot and come back again. So it's warm everywhere. Yeah, there's no ice. By 30 million years ago, however, this Tasmania Pass opened up, and the Drake Pass opened up from deep ocean. So circumpolar circulation started to be formed. Circumpolar circulation is a very, very strong current. For example, everybody knows Kuroshio, right? Kuroshio is big current. How large is Kuroshio? Kuroshio is about 30 Swerdrop. Each Swerdrop is 10 to the 6 cubic meter per second. Yeah, 10 to the 6, 1 million cubic meter per second. So Kuroshio is 30 million. Gulf Stream, the current flow over here, it's 50 to 60 Swerdrop. Double Kuroshio. Yeah. How about this current? This current is 130 Swerdrop. It's such a strong current that it effectively isolates Antarctic. Once this Tasmania Pass opens, isolated. So the South Pole becomes so cold, and the ice, permanent ice form over there. The North Pole is not. Not only is not that. Look at this region. Look at this region. Look at this region. This region. Eventually all dried up, becomes Mediterranean Sea. Yeah. This shallow ocean has been there for tens of millions of years. Yeah. And because of the formation of this shallow ocean, lots of the died marine organism accumulated and becomes oil. So all this region are oil rich. You can look at Saudi Arabia and Iran, everywhere it's over there. Yeah, the shallow ocean part, it's the part that you can possibly find. This is called oceanic sediment. Yeah. So this part is actually the part that it's shallow. Now, by the same token, all this part is shallow ocean. So all this part has a very good potential of finding some oil or gas at least. Yeah. That's why people are so anxious about climb this region. So all the shallow oceans are rich, potentially rich resource area. Another possibility is North Pole. Yeah, North Pole is always shallow. The North Pole is not as productive as here, but nevertheless, it's always there. So it's been collecting. So North Pole, the Northern Ocean, is another potentially very productive region. Yeah. Anyway, by the time to about 5 million, this used to be Pacific Ocean and the Atlantic Ocean used to be connected. By the time of 5 million, Panama Isthmus raised up, separated the Pacific and Atlantic Ocean. Now Pacific and Atlantic Ocean, the water height, it's totally different. And that's why Panama Canal need the ship locks. You have to go through, climb up and climb down. Yeah. Once this sealed up, and the Bering Strait also sealed up, and the Northern Ocean get isolated, the ice start to form over there, about 5 million years ago. So all of this, you can see that if you look at the temperature actually, from about 4 million years to now, it gradually decreasing. We are now here. Yeah. This little fluctuation, don't think that's not important. That's the big events on Earth. This fluctuation, all this fluctuation, you think are noise. These are not noise. Looking at this, you can see these are not noise. This actually, if you do a spectrum of this, what people, of course, before they know HHT, they only know spectrum. We do spectrum of this set of data. You find this is a peak of 100, 100,000, 41,000, and maybe something like 20-some thousand. Yeah. So you do another section, you again find 41,000, around 100 and 400,000 years. Yeah. So this fluctuation, what are these fluctuations? These fluctuations are ice ages. We have ice age start from the last 1.5 million from now. Every 100,000 years we have a ice age. Yeah, and before that, the 100,000 years is not as prominent. More prominent is more like 41,000. But this 41,000 is not important because there's no ice. Yeah. Here we have you get in and out of ice age. In and out of ice age is big events in that. What caused it? Caused it is actually the Earth's rotation, Earth's orbit. Yeah. The Earth's orbit as we learn, the Earth's orbit is very regular. It turns out the Earth's orbit is chaotic. Chaos. Why it's chaos? Because Earth rotates around the sun. Its dominant influence is the gravitational field of the sun. But then it has a moon. So moon also has a gravitational field. And that causes perturbation. And that perturbation, because it's so close to the Earth, is small. And it's small, what it has caused? It caused the 19 and a half years Metonic cycle. Yeah. So the Earth and moon wobble together like a twin, but a big brother and a small brother. So it's small. But what else causes it? Every little mass causes perturbation. The other planets, Jupiter included, yeah, all cause perturbation. Because all this orbit has its own periodicity. This periodicity is not like a 1, 2, 3, 4 or even numbers. None has even numbers. So when you compute the orbit, you have to consider all the masses. Now, people start to consider the little planets in the belt. Consider that mass. We can compute the orbit of the Earth to 35 million years. Yeah. If you compute it beyond 35 million years, you can still get the period right, but you get a phase wrong. The phase is very important. You don't get a phase right. But those are the small change. The largest change actually is caused by the sun. Eccentricity. Earth rotates around the sun, around a elliptical orbit. But the eccentricity fluctuates like this. Each of this is 100 million years. Each of this large cycle, 400 million years, roughly. Yeah. And beyond that is the obliquity. The obliquity is the inclination of the Earth's axis. Now the Earth inclined at 23.5 degrees, but that fluctuates between 24 and 22 degrees. They fluctuate. This is about 41 years. Yeah. If you go beyond that, then it's the wobble of the Earth's axis. It's called precession. The precession is around 23 years. If you look at this data, you find that the Earth, the climate, can actually move in and out. We now move in a period dominated by eccentricity. Previously, it's dominated by the obliquity. Yeah. So we don't know why it suddenly switched to another state, but it did switch back and forth. So if we look at this our last 100 years, the last 100 years data, as I said, based on this, you can draw a straight line, draw another straight line, draw a series of straight lines. This straight line made IPCC people conclude that our global warming is accelerating because it's flat, steeper, and the steepest. Yeah. But this is because they don't know trend. Yeah. They know that for shorter recent period, the slope is greater, indicating accelerated warming. This is in the fourth assessment, 2007. This is the stuff that won the Nobel Peace Prize, not the Science Prize, Peace Prize. Yeah. That you should know that the slope is computed by del x del t. If you change del t, it's going to be the value is going to be bigger if you shrink del t. Yeah. The shorter you get, the steeper you are. So it's not surprise that we will do that. And see, there are two issues. The primary issue is how to determine the rate of increase. The second one is what is the trend. The trend, state of the art of the trend, is that the one economist trend is another economist cycle. This I quote from the book by Engels and Granger. Engels and Granger are Nobel Prize winner in 2003. Yeah. And in their book, Long Run Economic Relationship, this is what they say. Well, not what they say, but one of the author, Watson, very famous economist, is one economist cycle, one economist trend is another economist cycle. What happens in the in the scientific community? There's a problem on determining trend, and the problem on determining the trend. The other word of the trend is regression. Yeah. How can I draw, if I have a scattered point, how can I draw a line through that, or something to through that, to indicate the relationship between the two variables? Yeah. This is called the regression. The regression, let me see. There are two dominant schools fighting among themselves of how to determine the regression. One part says that you have to give a functional form. The most popular, 90% or 95, 99% of the trend is determined by straight line. All the statistics are built on straight lines. It says, whatever you got, draw a line, straight line. Straight line is very easy to draw. The people that claim that we should either draw a straight line or whatever line is that this is the data is already complicated enough. We should make the same things simple. So straight line is the simplest. And beyond straight line, you can draw polynomial. Yeah, quadratic, cubic. You can even draw exponential. But whichever form you select, people can always argue why you choose cubic, why not cubic choose quadratic, yeah, why not choose quadruple. Yeah. There are always arguments. So all right, forget it. Let's just draw straight line. So 95, 99% people draw straight line. Yeah. So the statistics is built on straight line. But the other group says, once you draw straight line, you already predetermine the relationship. The relationship happens to be linear. Okay, we should not do that. So the other group, equally famous, and is gaining more and more dominancy, is that they call the non-parametric determination. The parametric means I determine the functional form. Straight line is very simple. A, t plus b. I only have two parameters, a and b. Once I determine a and b, I'm done. So then you can build all kinds of statistics on a and b. This is what's the scatter of this. The other school says there's no way that all the relationships are linear. Now, how to find the nonlinear relationship? So they use I will smooth the data. Like, for example, like this. I'll smooth it. This actually is smoothed time series. They use 20, 30 years to smooth and get the time series. And if you use 10 years to smooth this, and you have 20 years to smooth, the more you use, the smoother it becomes. Eventually, it becomes a very smooth line. And if you get that smooth line, I say, well, that's the regression. That's another possibility. Smoothing is a very powerful way, but over how large a window? It's a problem that you have to determine. Smooth is a very good method. Smooth is adaptive. It's determined, the result determined on the data. Yeah. Only thing is the smooth, the length. But turns out that smooth, you think that if I use 10 years period, I will not influence higher frequency, the longer period. It's wrong because the harmonics. So smooth, in the spectral analysis, smooth is a very sharp filter. Yeah. So the other school says we should use smoothing. But because you have to determine the window width, you have to determine how many times you smooth, and the shape of smoothing, whether you use flat smooth or some sort of curve. So there are all kinds of different kind of issue comes in. So that's why if you now look in the research area, you see the big book called the Nonlinear Time Series Analysis. All talk about smoothing. Yeah. Which window shape, which window length, and because it's window, there's very good theory that you can come with. What kind of shape give you what kind of influence. So this is the status of trend. Nobody knows how to draw trend. Now, because of this confusion, I think this is all fit in this saying, 名不正, 名不正. I hope my colleague in Japan can read this. Yeah. 名 means name. In Chinese, it also means definition. Yeah. If a definition is not proper, and then talk, your discussion cannot be smooth. Yeah. And if discuss cannot be smoothly conducted, nothing can be accomplished. Yeah. Basically, what this is saying. This is by Confucius. Yeah. Confucius already anticipated. If you do not have a good definition, then there's no way that you can talk smoothly about the events. Yeah. So the rough translation is, without the proper definition, logic discourse would be impossible. Without logical discourse, nothing can be accomplished. Yeah. Or nothing can be agreed upon. I think the trend, the definition of the trend, should not be determined by preconceived line, nor by a smoothing. Yeah. So I have done twice, I discussed this twice. Once in the Proceeding of Royal Society paper, I talk about it. Then later, I joined with Zhao Hua Wu. We wrote another paper in Proceeding of National Academy of Science. So we published in the British National Academy of Science and American National Academy of Science about the trend. How to define trend? Here we say, given this, you have to give me a span of data. Trend only appears locally relative to your data. Trend does not float around. Yeah. So in a given span of data, trend is intrinsically fit to the monotonic function. Yeah. Monotonic function means it's either increasing or decreasing. It does not fluctuate up and down. That's monotonic. Or a function which can be one extrema. You can go up and down. That's a trend because it did not come up again. If it come up again, then it's cycle. Okay. One extrema. If a two extrema is half a wave. Okay. Here, the important word is local and intrinsic. What is intrinsic? Intrinsic means inert. It belongs to the data, part of the data. It's not imposed upon. When you impose upon something, it's it's called extrinsic. Yeah. For example, we look at the data like the global warming with a straight line. How do you know the global warming is straight line? How do you know the global warming is linear? If it's not linear, you impose on that. That's extrinsic. That's not intrinsic. Okay? It has to be local. I take a section of data, I can give you a trend. But if I have a longer data, the trend may becomes part of the cycle. True, what they say, the one person's trend is another person's cycle. If you talk about different length of data, if the data is the same, then everybody should agree upon a trend or a cycle. Yeah, so this intrinsic is in contrast of extrinsic. Anything that you impose upon the data are extrinsic. You say that, okay, this is what I, linear, quadratic, cubic, quadruple, whatever function, they are all imposed upon the data. The data didn't say that. So, so the operating word, important words, is intrinsic. How you determine intrinsic? The intrinsic mode function is intrinsic. It belongs to the data, it's part of the data. So the trend has to be that. And then, so the operating of determined trend is not by parametric fitting, not by smoothing. It's by removing cycles. How you determine cycle? I have two extrema, maximum, that's one cycle, I take it out. Anything has maximum, minimum, maximum, multiple maximum, it's a cycle, I remove. So the way to remove that is EMD. So using EMD, we get a very natural way to remove the cycles. And what's left is the trend. So, so this is our definition of trend. The definition now, we do give a definition. Yeah. Previously, there's no definition. Then you may ask, is why should I worry about trend if I'm not worried about the relationship between two variables? We do worry about the trend even when you do statistics. Not all the data are zero mean or flat or whatever. When the data has some up and down, large fluctuation, that may indicate a trend. And that, if you don't take away that, then the even spectral analysis is not possible. Yeah. If you have a trend, probability density is also impossible. Yeah. Probability theory is built on global property, not local property. Yeah. If you have a trend, the distribution is biased. It cannot be fair. Yeah. Somebody is small but sit over here. Somebody is large, sit over here. So then this value is higher than that value. It's not fair. Right? So you have to take this out. To take that away, it's detrend. Detrend means to take a trend away. If you don't know what is trend, how can you detrend? Yeah. But now the statisticians has a cheap way to detrend. Take a derivative. Yeah. Take the data, take one derivative. They say, all right, this trend's gone. That operation is only good if the trend is linear. Yeah. A, T plus B. Take a derivative becomes A. So no more trend. But if the trend is not linear, derivative is not going to do it. Yeah. Take any data, try to take a derivative, see what happens. Yeah. It may get near zero mean, but it's not without trend. Unfortunately, that's most people are doing that, especially in financial area. The financial area, they don't tell you that they did the derivative. They say that we don't study the spectrum. We don't study the market. We study gain. We study gain. What is gain? Gain is more. It's more horrendous. If I have x of t, which is my stock price, I take log. Yeah, and then I take a derivative. So what that give me? That give me time derivative x divided by x. Yeah. So that means all the stock market they'll talk about is that today's price difference with yesterday's price divided by yesterday's price or today's price. So that's gain. It's very sensible. Not only very sensible, it's very sensible to the stockbroker, because stockbroker would like you to sell and buy every day. Each time they will get a little bit commission, right? So if you hold the stock for 20 years, then what will the stockbroker do? Nothing, right? So they will be they will be out of job. So if you talk about gain, we talk about short-term derivative. And because of this, people get into the habit of not looking at the very long trend. All the people talk about stock market talk about short-term fluctuation. Yeah. And because of that, because of this, another thing happened is that all the financial people all start again. All the statistics model on finance are built on gain. Yeah. When it's once you take derivatives, almost look like a stationary time series. So people say, if it's a stationary, it has to be ARMA. If it's not ARMA, ARIMA, yeah, integrate once. So all the economic theory and everything is actually built on stationary time series. Yeah. None of the data is actually talking about non-stationary time series. Yeah. The one consequence of that is people don't think of long term. Yeah. People think of short term. And that's why I believe it's part of the problem. The better the more dominant the current economic thinking is, the shorter they think about the terms. So as a result, in United States, I don't know about Taiwan, United States, there's a very good job, a good career. It's called a consultant. Yeah. The consultant, the people doing consultant are the smartest people. Yeah. People, you can be a engineering major, it can be a science major, being whatever major, going to the top school. Yeah. Once U.S. News and World Report, I believe, or Newsweek interviewed a bunch of engineering students at MIT, at Carnegie Mellon, and all this top engineering school. So you study engineering. What are you going to do? Are you going to be an engineer after you finish? No. So what are you going to do? I'm going to be a consultant. All these consultants are young graduates from top schools. They recruit by the consultancies, the consulting company. Yeah. The consulting company gives them very basic training, and then send them out to the company to advise the company how to do business. In the United States, I have a lot of friends, good friends. All their kids are consultants. The quote unquote the better ones are getting from top school, go out to work for a couple of years, and then go back to get an MBA. Yeah, MBA, it's get them unified, very uniform. They all think the same. What they do, they learn how to look at the company's book, and they can spot which part is lose money, which part make money. So the decision is that the part that lose money should be get rid of. The part make money should be kept. Yeah, and then after they juggle the book, the company becomes profitable in short term, not in the long term. As a result, many of the companies get gutted because all the vital part was sold. Yeah. I think this may have something to do with this. May have something to do with not knowing trend. If we look at the trend in the long term, then you know they are cycles. They are long times climbing or long time decay. There are reasons. Not everything is in the short time derivative. Yeah, I sometimes I watch television here in Taiwan. Lots of people talk about trend. They also draw this upper and lower envelope, but not like us. They draw straight line envelope, right? This is upper, this is down. So when you heat up, you have to sell. When you heat down, you have to buy or something like that. Whatever. Anyway, this is my view of trend. Trend, let me emphasize, should not be determined by regression, parametric or non-parametric. It actually should be determined by successively removal of oscillation. Yeah. So if we do that, if we take this data, and this is the our Earth's global surface temperature anomaly. This is the ocean data. This is the Atlantic Ocean, North Atlantic Ocean average temperature going up, down. This up and down has been used by people as an indicator for climate. This is a warmer period, this is a cold period, warmer period, cold period. The cold period in 1970s, 1980s were cold. And then we're now warm. Now, there's a cycle. There's a cycle here. The cycle is around, at that time, they were talking about 70 years cycle. The 65 to 70 year cycle. This is a Nature article in 1994. Yeah. So this cycle, it's known to many people, but it's ignored by the straight line drawers. Yeah, if you draw a straight line, of course, you ignore the cycle. Let's see whether the cycle indeed exists or not. This is the data. I take the January, February, each month time series. January time series, February time series. Each of that, I do a EMD. There are 12 lines. So all 12 lines say that this is a cycle. And a very dominant cycle too. Yeah. This is from the surface temperature. Yeah. So looks like this is the trend. Yeah. Then if I check this data, I find that 1, 2, 3 are statistically no difference between noise. But the fourth one, it's way and above that. The fourth one is what? Fourth one is this. See, this 3 looks like a noise, but this one is not. Statistically significant. Okay? So we have that. Then we look at the ocean data. The ocean data, again, 1, 2, 3, and a big cycle. And ocean data, the trend disappeared because when they do the ocean data, they are smart. They took away a straight line trend. So there's used to be a straight line trend, took away. It only has a whatever left. Yeah, flat left the thing. But don't worry. Let's check the significance. 1, 2, 3 is no difference from the noise. But look at that. That's the statistically significant component. It's the force. Now, when we take that, we check the period. For the surface temperature, the period is between the lowest is around 60, the highest is around 80, the average is 67.5. Yeah, years, average, total mean. Yeah, there are scatters, of course, but the average is around that. And if we look at the ocean is much more stable. Yeah, ocean is much more uniform. There's less noise. So look at that. average is 65.5. 67.5, 65.5, around 65, between 65 and 70. Yeah. So this is the ocean. And if you take the force component of each one and you do a correlation, you see what is the correlation? The correlation is 90%. So the ocean temperature fluctuation and the Earth and the global surface temperature fluctuation, 90% agreement. And not only that, if you take that component and run a correlation regression on the temperature station everywhere, because now we have temperature station here, every 1 degree or 2, we have one average. You run that, you find on land, the trend, this is the secular trend. The trend, secular trend, only on land, only high latitude, the temperature indeed increase. So the global warming, the most significant signal is in high latitude. See, around where we live, most of the region, on land, there's almost no signal. Yeah. However, if you look at the ocean is totally different. Everywhere the ocean temperature increases. Yeah. The reason that the land does not show that much is the land heat capacity is much lower than this. So the ocean, most of the ocean temperature is increasing. This is the trend. Here is the trend. That multi-decadal fluctuation of 65 years on land, nowhere has that, except that in eastern China has a little bit, and in the United States has a little bit. Other places, very weak 65-year cycle. But in the ocean, it's extremely strong. Here, we have a very strong warming. Here, we have very strong cold. Yeah. In the ocean, the cycle, warm, cold, north and south has a seesaw, coming up and down, coming up and down. Yeah. So this is the large picture. Is the global warming? Yes. Where is the warming the most strong signal? In the ocean. On top of the general warming, there's another 65 years to 70 years fluctuation. That fluctuation is north and south asymmetry, seesaw. Now, the details. When people say that if the IMF component is no difference statistically from white noise, we can throw it away. Don't do that too fast. We should examine that. After we remove the trend and the 60-year cycle, 65-year cycle, this is what's left. Can you see anything in here? Not much. Almost like white noise, right? This is the surface temperature. This is the ocean temperature. They both look white, and we can check it, see whether it's white. It's almost white, yeah. Within the data span, it's almost white. Means this data has no more information in it. And indeed, if we do a autocorrelation, spectrum is from autocorrelation. Spectrum is white, autocorrelation should be delta function, and vice versa, right? So the autocorrelation for AMO, for the ocean, is a delta function. Yeah, autocorrelation for the GSTA is a delta function. Now you think, I have a delta function here, I have delta function, they're all white. Do you think that the two should have a correlation? Two white noise should not have correlation, right? Generate the arbitrary white noise to see how the correlation. But look at what we have here. The two time series has a delta function cross correlation. Yeah, the cross correlation. This is 4. This is 5. This is the average is way beyond it. This is surprising. So a white signal should actually have very high cross correlation. That means there's something in there. So what's in there? So then now we do this. This is the trend. This is a 6-year cycle. This is the third, the fourth. The third, you start to see some trace, and by the time you see the third component, yeah, this is the you see very strong correlation with the local temperature. What is this? This is ENSO. Yeah. Yeah. This is ENSO. That short, that noise-like thing is actually this, and you can still see a little bit trace. Tell them that this is the wrong place. So, so the moral of this is that when you see something statistically insignificant, it's only statistically insignificant compared to others. It still may contain physical meaning. And the physical meaning here is very clear. The ENSO, El Nino, has a very dominant influence on the global climate. Yeah. We are here. We are strongly influenced by that. So is the United States. Is strongly influenced by that. Yeah. So, how about the warming trend? The warming trend actually should be this. After we remove all the cycle, and they'll talk about warming trend like that. They'll talk about drawing curves here, here. Now, if we want to challenge them, they say, all right, draw 25 years slope. You draw it here. How about I draw it here? How about I draw it here? If I draw 25 years cycle, 25 years slope everywhere, what should I get? You get this. This, what is this? This is, I draw 25 years slope everywhere, center everywhere. And that center everywhere, this is the range. Yeah, this is the mean of 12 months. Of 12 months. And this is just annual cycle. Yeah. What you see here is that if you start to draw 25 years, the 25 year cycle has actually, 25 years trend has a cycle. What is this period? 65 years. Yeah, so 65 years is indeed there, no matter how you draw it. But their straight line trend, this is 25 years, this is 50 years, this is 100 years, this is 150 years. Yeah. If you take this curve and average it over 150 years, is that. If you take this curve, average 100 years, it's like that. 50 years, almost like 25 years, almost like that. So to me, it seems very clear that the global warming has a trend, has a dominant cycle of 65 years. No. The argument or the current mainstream wisdom still say this is wrong. We shouldn't look at this. Why we shouldn't look at this? Because the degree of freedom is not high enough. Yeah. The degree of freedom is only have one wave, only have two waves. Yeah. So what if we throw away this two wave, this data is not very good, it's throw away that, you only have one wave. The one wave does not make a case. Yeah. That's their argument. Let me see if no, I did not bring. I should have another view graph. I forgot to put it here. Another view graph is done by, I don't have my own computer. If I have my own computer, I'll put it. Another paper is in 1975. 1975, Wallace Breuker. Wallace Breuker is the person coined the term global warming. The global warming 这个词啊 is proposed by Wallace Breuker. In 1975, he published a paper. And this paper is I may be able to find that paper. Wallace Breuker in 1975 published one paper. The paper is in Science, not very long paper. This is Are we on the brink of a pronounced global warming? Yeah. This paper, I admired him very much because this paper was published at this time. The temperature is after high and getting low. It's at this point. At that time, the newspaper will not talk about global warming. We'll talk about ice age. Because everybody know by then, the ice age come every 100,000 years. We're overdue for another ice age. Yeah. People think that this temporary decreasing indicating that we're sliding into an ice age. And at that time, he came out and said, oh, global warming. Not only that, he coined the word global warming, coined the term global warming. And that is great because if you buy stock, you should buy it here, right? And then you have an increasing. He has the foresight and the fortitude to say that. And why he say that? He said that based on, this is Greenland, based on Camp Central data. What's Camp Central? Camp Central is a ice tunnel dig into Greenland ice. It was operated from 1959 to 1960. And this place is 800 miles from the pole. The temperature is minus 70 degrees, and the wind is in exceeding of 125 miles. It's very horrible place to dig a hole in there. The hole looks like this, huge hole. Who will spend money to dig a big hole like that? United States government. Why they want to do that? They want to dig a tunnel 4,000 kilometers in the ice. Why? They want to put 600 nuclear missiles in there to attack Russia. This is a Cold War thing. They start to dig a hole like, big hole like this. Yeah. But then they find that they cannot maintain it. The ice keep changing, and they crash this the tunnel. So finally they said, oh, forget it. We cannot maintain it. So they give up. They were there for 17 years. we don't know. We don't even know about this hush hush, top secret thing. Yeah. One good thing come out of that is the ice core. From ice core, you can retract the data. This is the ice core data from that period. Yeah. If we will get this data, I will be able to do something, right? When Wallace Breuker got it, he has no statistical means to analyze this. So what he did is this: from minimum to the next maximum, from minimum to next maximum, he just count each one. It's count from minimum to next maximum, 40 years, 25 years, 40, 25 years. He count every one of them and put a list. Every one of them put a list. Average, 35. Minimum to maximum, 35. So the whole wave is what? 70 years. Yeah. So based on that, he predicts. So that we are heading to a global warming. Yeah. And this is what he drew. This is the cycle, and he added a global warming trend, and he said, okay, we may be here, but we're going to go up and then come down up. Yeah. Wallace Breuker is the one claimed the global warming, but now he is somehow verified. He's a very famous scientist. Well, I think the most respect to the climate scientist, but now he got a little bit bad name because he said that the global warming is serious. We have to think about how to face it. One of the way to face that is to store the carbon dioxide. If we get too much carbon dioxide, we have to condense the carbon dioxide. Where to store it? He proposed deep ocean. And this get into controversy because the mainstream global warming people think that we should not study any means to sequester carbon dioxide. If you find a way to sequester carbon dioxide, you will not concentrate in cut consumption. So their only way to solve our problem is cut consumption. Yeah. If you try to store that, you take the attention away from consumption. You say, I can burn, then I can store the carbon dioxide in the deep ocean. So he's getting into some sort of controversy. So he's not in the press anymore. The press don't want to pay attention to him because he thinks that there might be a solution other than cut carbon consumption. Anyway, so this is another proof that we do have do have a 70-year cycle. We don't have enough degree of freedom. Wallace Breuker add 10 more. Yeah, so it looks like that cycle is there. The Wallace Breuker's time series is much longer than this time series. It's from ice core. Yeah. So I think the trend is very clear. This is the trend. Yeah. This is the derivative of the trend. This is the increasing rate. The increasing rate actually consists of a trend plus multi-decadal. And this, their increasing rate, and this is the increasing rate that we calculate. Yeah. And this is, if you add these two together, it's comparable to theirs, if you count both together. Something obvious like this, it's hard to get published nowadays. Our paper was eventually published after 3 years of review. Yeah. Just try to publish this kind of curve. Took 3 years. They get all kinds of problems. Yeah. finally we get it published. They challenge us any other way, we immediately prove that this is right. We immediately prove this is right. And even that is not enough. We finally published together with Mike Wallace. Mike Wallace is one of the same order of Wallace Breuker. He's at University of Washington. He's one of the most respected climatologist or meteorologist. To give you one indication of how great he is, after he got his PhD from MIT, he started to teach at University of Washington. This is the 40th, maybe the 40th years that he's teaching there. Last year was his 70th birthday. The university threw a big party for him, organized a symposium to talk about his accomplishment in climate. And at the banquet, the university announced, name a building after him, Wallace Hall. Remember, he didn't donate any money, he didn't retire, he didn't die. So most of the time in the States, they name a building after somebody died, after somebody retired or something, or after somebody give a lot of money to the university. They will name a building after him. He didn't qualify any of those. He's still teaching as a building, Wallace Hall. That's how great he is. Yeah. So we are together on this enterprise. We believe collectively, Mike Wallace, me, and Zhao Hua, and one of his students, we believe that the IPCC needs some education in statistics. But that's, it would take years for them to finally agree. The scientific community sometimes is not that objective. For example, solar, the influence of the sun. 10 years ago, there's a term, a very popular term called the solar constant. The sun has to be constant. So the radiation sent out by the sun is constant. Anybody challenge that is crazy. So the solar constant has been used for hundreds of years. Now they agree solar is not constant. Solar fluctuates. And if you look at the solar fluctuation with the climate, you'll be surprised. It was so parallel to each other. Yeah, but did the solar variation cause all the global temperature change? Perhaps not. But it's a very interesting problem for people to think about the solar constant. Now, if we use EMD, we can determine the trend, we can determine the cycle, we can determine the even closer, even shorter wavelength cycle. Yeah. This, we start to get into pre-ENSO. The next component will be ENSO. Yeah. So ENSO scale is around 2 to 7 years. So the global climate change is highly variable, and we don't know it well enough to actually say that one reason is the carbon dioxide, and that's alone. That, I think, it's too arbitrary. Okay, so here is another thing that you can see, that after we get to the plateau, we don't set records anymore. The global warming, we're now in a more flat region. And in the next few years, I think we may even see a decrease. And then may come up again. Yeah. The global warming, there is a warming trend, but there is also a natural fluctuation. So we now have a working definition of trend. It is a function of local time. Yeah, we have to use adaptive method to do it. Then we can determine the significance, and the significance itself is only statistic. Physical significance we have to actually look. Now, people may ask, so you talk about global warming. Do you know what will happen in the next 10 years? I don't know. I don't do predictions. Yeah. But if I extend the curve like what Wallace Breuker did, then I would say the next 10 years will be cooler than these 10 years. Yeah. Well, that's the lecture on trend. Thank you very much. Our colleague in Japan, you have any question about what I talked about today? Questions? I should look at that. If you don't have any question, then the class is over. All right? Bye-bye. All right. Now we can... Okay, we'll switch back to Chinese. 有没有问题？
这种就是几十亿年前的 data， 怎么去 verify 它的？比如说那个海洋的那个
sediment 是吧？
对，就是陆地的那个。
没有办法去直接证明呀。那么这个里面有没有问题呢？有问题。这里面问题，比如说我们现在可以去 calibrate 它，但是我们现在的 calibrate 都是用现在的同位素，现在的这个大气的这个含量啊什么去决定它的这个比例呀。然后呢，一切都是用现在的 condition 去 calibrate 它。过去这个大气的比例是不是这个样子？呀，也不是的，因为你知道，在6500万年问题比较小，你要再过远了，到了几亿年前，甚至更远的话，大气的 consistent 不是现在这样。我们一开始大气是没有氧气的，大气有氧气是因为有了光合作用以后才有的。一开始有生命的时候，这个大气是很多二氧化碳、很多这个甲烷什么这些乱七八糟的东西，氧气非常少。所以，但是6500万年呢，大气的组成跟现在差的不是很多，但是是不是完全一样，不知道。那么现在呢，最好的办法都是用这个同位素的 decay half-life decay 的办法，比如说我们 carbon dating 也是一样，你怎么去 verify 它这个是一定什么？那 carbon dating 呢，我们可以有一些东西可以去 verify 它什么呢？就是说，比如说你找了一个木头，这木头是商代的，呀，我们决定它是商代的，那商代有商代的历史，我们就知道它大概差多少，这个还可以。但是到了100万年的时候，没有任何的东西。但是呢，这个里面有一些间接的证据，比如说我们在这个沉积层里面找到了，那么大家估计这个沉积层的地质年代可以有一个大概的估算，就是说这个地质年代是什么时代的。这个估算呢有各种方法哈，除了这个 isotope 必须有什么氧啊，有碳啊，什么东西的，这个要生物才行，无生物不行。那么无生物有的时候就是用这个地磁的改变，那个也是一个很好的 clock 呀。还有其他的天然的同位素也可以做，像那个Atlantic Ocean 的那个 spreading， 它那个估算就是用天然的同位素，还有用它的 sediment， 就是我们沉积物的速度来算，这些都是大概的，都不是 exact， 但是这个大概啊都可以有一个相当，就是它不会 至少 order of magnitude 是对的，啊，这是不是 exact？ 就是说你说是6500万年，也不会是6400，不会是6300，这个 hard to say。比如说我们 ice core 的那个数据应该很准的 ，ice core 在这个 Camp Century 的 ice core 估算的非常准，因为它这是很短的 ice core。你要到南极的 ice core， 它的那个绝对时间大概6000年，也是用同位素6000年。OK， alright， 没有问题，下课。我把这拔掉了啊。